Okay, so welcome back to the database workshop. Um, so today we're going to continue looking at databases, but we're also going to very much try to get to our use case where we had a set of simulations to do and to analyze and to coordinate, and we wanted to use a database for that. And so the assignments that you will have to do is basically to complete what we're starting today in setting up this set of experiments, computational experiments, but nonetheless, and to use SQLite for that. Now we left off discussing some database design principles, and so I'll start back at principle one and just go quickly through them again. Um, and they're just best practices that will basically mean that you don't have to go back and redesign your database and re-enter all of your data somewhere halfway in your project because you then found out that you should have done things differently. So the more you can do things um, sensibly in the beginning, the less work you'll have later. So our first design principle was for every record to be unique. So we had our pets table, and we couldn't have any way to say or know whether this entry of Kitty, which is a cat of 3 years old, whether those are two kitties or not. And so one way to at least encode that is to say that every record should be unique, so that if I tried to enter the same pet again, it would give me either an error or just overwrite it and but not have two entries there. So the way to do that is to use a key. So you use a primary key. It's called primary key, and the key has to be unique. And almost always, but not completely always, this is an integer and it starts at 1. So if we wanted to create this table with an ID, all we need to do is add an extra field that's called ID in this case. You can give it any name you want, but you have to flag it not just as an integer or define it not just as an integer, but say primary key. And then whenever you insert something and you don't give a value for this key, so you give it null, it will insert the next value. And so here's a way to build this improved table with an ID. So all of these IDs will be automatically filled. Thirdly, um, or the third principle, you'd want your records to be things, to be entities, to describe something, rather than just a fake collection of data points. So for the pets table, that was fine. The simulation data was a mixture of parameter values and job outputs and measurements and other details. And so that would require to be a little bit differently. Um, and this is generally what you want to do. You want every record or every row. Remember, records and rows, they were the same thing. You want them to be things, right? And then it makes sense to imagine every table to be a set of things. Uh, okay, the fourth principle, and I think this is where we left off, is to try and not duplicate data if it means the same thing. So here we have cats twice and dog twice, and it's not for optimization or efficiency so much because these are very short words, but more to have a way to codify that these are the same type and not just different types that just happen to have the same name. And so how would I do that? Well, I can use what's called foreign keys. So I'm going to encode every type as a key. It will be an integer, and I'm going to put those in a separate table. So cats are associated with the integer 1 and dogs with integer 2. And now whenever I have a 1 in my type ID column, I know it's a cat. And because these are the same keys, I know that they are I know that they are the same type and not something that happens to be called the same. Now, you want to make sure that this type ID column here is one of the values of the type IDs here in the pets2 table. And so to do that, that's when you call a foreign key. So these have their own keys. These are the integer primary keys of pets2. I want to express that type ID in pets refers to a type ID in here. And so the syntax for that was to, in the definition of your table, so when you create the table, you have your list of column names and types, right? But then there's an additional line that should say something like foreign key, and then the name of the column that should be pointing to or referring to a value in a different table, and then references, and then that different table's name and the different table's column, or whatever the key is called in that other table. So this is the is what would do this. So we've got our pets2, which is very very straightforward. But then we have pets itself, where we have a type ID, and we say that the type ID references pets2 type ID. Okay, so now those two are linked. Now, to make that work within SQLite, we have to switch on the checking of foreign keys, because otherwise it actually will ignore that and will allow you to basically put any integer in this type ID column, even if it's not in the other table, because we haven't switched on this capability of checking foreign keys. So the way to do that is pragma foreign keys equals on. So once we have these tables, we could insert things into pets. And I think last time this example had the values of the type ID for cat and dog hard-coded. You don't have to do that, and you typically don't want to do that. You probably want to insert cat, and then when I insert cat, and I'm only inserting the name, what it will do is it will create the primary key itself. And so if it does that, I can, okay, so it does that, but now how do I know what value it put into the type ID? And so once I've executed something, remember I get this cursor back, there's actually information in that cursor. And so one of the informations when you do a single insert is what the ID was of the last row. And it goes like dot last row ID. And so I assign that to cat ID. So that is the value of my type ID after I've inserted this, this row. I do the same for dog ID. And now when I insert the pets, rather than having hard-coded numbers, which might change or I might not know beforehand, I just refer to them by their name. Okay. And then commit. So I have my two tables. They're linked by foreign keys, and they are, yeah, they're there. The values are in there. Now, if I want to construct the original table, that is to say the table where I have my pets and the name of their type in it, I can do that, and I had to use this join. So I joined the two tables together, but I make sure that I only join those rows where the type IDs coincide. So that's the on pets dot type ID equals pets2 dot type ID. And that gives me, again, this cursor. And to get all of the rows back, I had to do fetch all. I think that's where we were last time. There's a few more. There's a few more principles. One, I mean, that's sort of a principle that is true for any programming language or almost anything you do, where you have to give a label. Use clear names. So the table names and the field names should reflect what they are, and should make it easier for somebody that is just handed a database to understand what you are storing. So it should be unambiguous. You don't want it to be too long, because you're asking for typos, right? But keep it to sort of plain English, English being often the most common language among collaborators, but plain language in any case. Avoid spaces and special characters or reserved SQL words. So don't make a table with a column name that's called select. That's going to be, at the very least, very confusing, even if you can make it work. So don't do that. Spaces, again, in SQL, spaces have meaning. They separate keywords. So you don't want that, no commas. Just keep it fairly simple and stick to some convention. So if you like underscores in your names, that's fine. Just stick to that. Don't use a mixture of just gluing words together and underscores and maybe something else. Now, we've slightly deviated from that in the example. So for instance, we had a table called pets2. That's not a good name because it doesn't tell me anything. It actually sounds like it's yet another table of pets, and it wasn't. It was a table of types of pets. So a better name would have been pet types. Even the age was somewhat ambiguous because was that days, months, years. So if this matters and if it's not entirely clear from the context, you could encode that in the name. You could say it's the age in years. Resist the temptation of abbreviating everything. Just because it's easier for you to write, it makes it harder to understand later what's going on. So don't have a column that is called CPP0311. Who knows what that means? You might know it when you define it. You might not remember later. Say it meant whether a piece of code is C++ 3 or 11 compliant. Express that. It's a bit longer, but it makes it clearer what you're storing in there. A sixth one, and this is a tricky one from scientific computing point of view, is that column values are supposed to be what's called atomic. So just as one row is one entity, each column value should be one thing, in the sense that if I shouldn't be able to change individual parts of it. It should not have parts, basically. So thinking of, for instance, an array of values or a list of values, that's not something you should put in a column. The databases don't really handle it well. You'd have to encode it in some sort of way. Maybe you'd have to store a string. It's not a great idea, and it makes thinking about the data a little bit more difficult. But we do encounter lists and arrays and grids quite frequently in scientific applications, and what that points at is that you actually shouldn't be storing those things in a database. You could have some sort of file name stored into your database, and then that file under that name would have your binary data of grid points or what have you. So that sort of gives you a good indication. An example of when you might want to store something that looks like an array but really isn't, is still atomic, are, for instance, coordinates, like coordinates on the Earth or coordinates in a 3D space, because they mean one thing. They mean a point, but they're sort of the crossover case between what you might want to store, because if you think about it, you could store the X and Y values separately in columns in that case anyway. The thing with lists, in particular arrays, is that they tend to not have a fixed size. So you can't, you have to define your tables with specific columns initially. So you can't say, well, now I just need extra columns because my grid is larger. It just all shows that that kind of data doesn't fit in a database and really shouldn't be in there. It doesn't have to be there. There are better formats for storing that data. You can still use your database to catalog that data, but not to store it itself. Okay. Any questions about sort of the generic database principles? No? Okay. So let's continue and see how they pan out. So we're going to look at this, what is essentially a parameter sweep of MD, of molecular dynamic simulations. So we had this set of atoms They were argon atoms in this case, and we have a Lennard-Jones potential between them. That's the way that they interact, and that will tell us how they move. And with that, we can simulate a gas of argon with given number of particles, given density, given temperature, and see what the pressure is. So that was our goal, to see how the pressure of this argon gas depends on density and temperature, and we do that by simulations. Now, we'd want this as a function of temperature and density, which means that we need a whole bunch of simulations at different densities and different temperatures. We will want to record intermediate measurements. We will get the, we might want to vary some things that might depend on how many particles we take, how big the container size in the simulation is, what the temperature is. All of that could lead to quite a lot of data that we have to keep track of. Right now, we're going to be varying the density and the temperature, but we might want to vary other things as well. And so it could lead to essentially a rather high dimensional data set. But we want to be able to access that data set and select data points at, say, given temperatures or a range of number of particles. So the kinds of things that we would do with a select statement. So that means that we want to store as much as we can about these simulations in a database. But you can already imagine that the positions of all of these atoms, that's a list, probably shouldn't be in the database. Now, whenever you're faced with something like that, I find it very helpful, and I'm sure some of you are doing this too, to actually draw out your workflow. You have, and if you ever had to explain what you are doing, what your project is, to someone that isn't involved in the project, you're probably standing in front of a blackboard, or you have a piece of paper and you're just drawing it, or maybe a whiteboard online these days. But and that's important, because until you kind of know what all the moving parts are of your project, that's how you know how to automate that. And while the database part here is basically a record-keeping device, on top of that, you'll need some sort of scripting to automate that and to be reproducible. So when I'm drawing this out, at first, I just imagine a very simple setup where we have a set of parameters, and they're going to be density and temperature. But a set of parameters, and each parameter set leads to a simulation. So you think of every error here as a simulation, and that leads to some output. The output is the trajectories of the particles, and it's the measurements of things like pressure and energies. Now that is true. This is the computational part of it. And then after that, we might want to take this output and make some plots, or archive it, or analyze it in one way or another. So that's great, but we have to get this set of parameters somewhere. We have to coordinate the simulations and somehow store this output in a way that we can keep track and keep a handle on it. So given our set of parameters, that's our input, we'll create a bunch of scripts that can do the actual simulation. And so that's an automation step. But now, the same is true on the other end. Once I have my output, I probably want to create a script to do my plots. By the way, if you're not making plots with scripts yet, do start, because I can tell from experience, having to change a plot after you, say, submitted a paper to a journal, and they said, well, you know, those axis font sizes are too little, or the colors aren't right. If you did this graphically, interactively to create your plots, it's going to be a nightmare to reproduce most of it and just change a little bit. Whereas if it's a script, you probably just change one number from 14 points to 18 points and run the same script, and you get your plots. Much easier. Anyway, a little beside the point, but you will have scripts on the other end to deal with the output. And then each of these lines, each of these simulations that the script is supposed to execute, can itself be fairly complex and contain things. So it could have, in the most straightforward case, each run is its own batch job. So you're running this, say, on a supercomputer or on a cluster. You have, in the case that we will see, we'll have 100 of these jobs to do. Each job could be its own job to be submitted into the scheduler, whatever scheduler the cluster might be using. So that's a batch file. It will probably contain some sort of input file. Maybe that is the set of parameters for this specific simulation. That will go into the run. The run will produce a trajectory, maybe some other outputs to screen. Maybe there are some errors that might come out that we also have to catch. So for each of them, we have to catch those, and they become part of the output. So the batch file I didn't specify because it really depends on the scheduler you're using. We'll be using the teach cluster, which uses a scheduler called Slurm. If you've worked on Niagara or you've gone to some of our other training sessions, you might have worked with it. The input file for this case can actually just be a set of numbers, but it will contain, for instance, the number of particles, the density, the temperature, the runtime, the time step, and maybe some other things. So there will be one of those for each of these parameters in principle. And then they produce trajectory files that go somewhere. There's some outputs that exist somewhere. The last line of the output for our case will have all the averages that we're interested in, but we'll get all of this output anyway. Where do we store this, and what should we store in a database? So this is the workflow. It's not terribly complex, but it's still complex enough that if you wanted to store things like this in the database, say this is automated, and especially because we're running on a batch system, not all of those runs are going to run right away. Some might have to wait a little while, so we might want to keep track of what has run and what hasn't. We might want to do partial analysis at some point. We kind of want to have a handle of all of this. So for this assignment, we'll be trying to put as much as possible of this workflow into a database, and just see where we end. So what should we store in a database, but also what shouldn't we? So the question there, we can go back to the ideas of the database design, is what things are there? Because every table should contain things, because every row was a thing. What are the entities? What are the basic components that we have that we could store data about, or that we at the very least, when we have like lists and arrays and binary data, that we could store a file name of, say. Okay. And then once we know what the things are, what are the attributes? And how are they linked? Do we need any foreign keys to link things together? Those should be the questions when we are trying to design a database that can hold the information of this workflow. So I thought about this, and it's not entirely unique how you do this. And some of it is taste, some of it is experience, some of it is might be trying too hard to put everything in a database. But as I said, that is just the nature of the example here. So here are some entities that I thought of as putting in. The definitions of the parameters. So we have a system. It is defined by things like temperature and density. We could put those definitions in the table. So that gives us the parameters that are present, and then let's go to the workflow again here. So that's what is present, but then we will want to know what kind of range of parameters are we taking to generate our input. So basically the range of densities and temperatures, what are our initial values that we put in there. And maybe you also want to store how many intermediate values you want. So imagine that we want to do a scan. How fine range should the scan be? So the ranges of parameters and the numbers. Then once we have those set, that is sort of the workflow before we generate our actual input files. From those, we can generate the actual parameters we're going to use for jobs. So the input parameters, the exact value for each of the simulations. So that's one thing, that those are input parameters for it. Those aren't the same thing as the simulation itself. Those are separate entities. They run at some point. They produce some output. So we can call those jobs. So each of these runs here. We'll call it the job. So the input parameters are stored somewhere. The job produces something else. So the job will have output. And so we could call the output measurement. So whatever measured quantities we have, we would want to store them as well. And the measured quantities depend obviously on the parameters that I use. So you can see that there will be likely links between the different tables, like foreign keys, where the table of measured quantities will have some sort of ID that points back to the job that produced it. That might have an ID that points to the parameter set that was used. So we can imagine that. Does that make sense? Questions? Okay. So we're going to do some steps. And I divided the sort of the assignment into 5 steps, but I'm going to do the first 3 steps along with you because you only have really a day to try and come up with something that you can submit. And the due date for the assignment will be tomorrow at midnight. And just to clarify, that will consist of you producing 2 Python scripts and to submit them to the education site, and that they don't have to be completely correct or even completely working. Although it's nice that they actually run without errors, but even if they don't quite do what they want or they're only partially, I just want to see that you played along with the material. So do we have the? Let me show you the code where to get it, because we had that last time, but it's worth looking at. So the first step is going to be producing the parameter definitions. And this is one of those steps where you might go, I don't know if I need that. I can just write it on a piece of paper, and maybe that's true. But we're going to store it in the database anyway. So we are identifying a number of parameters here that go into any simulation. There's the density, there's the temperature, there's the number of atoms that are actually present in the simulation, how long we're running for, the time step, and the seed. And I think there might even be another parameter that I forgot here. Okay, so by having these stored and maybe the range of things that we want them in, that can help. Exactly, burn-in. I'm forgetting about burn-in. Thank you, Melina. Yes, so the burn-in, I think somewhere along the lines in the slides, there is burn-in. But yeah, so how long do we wait for equilibrating the system before we do anything? So now some parameters we are going to keep fixed in our example, but at some point you might want to vary them, like the number of particles. It might be that you get much better results if you have more particles. You will get less fluctuations, so that is the case. And so they might vary at some point. So we're going to store the parameters and their sort of lower and upper bound. And when the lower and upper bound are the same, we're going to say that that's just the only single value we're using. And I'm not entirely happy with that choice, but that's the choice that was made, and it's okay. It's workable. So we want to store this in a table, and that is possible. We can do that. So here's an example of how you might do that. So we're going to create a single database to hold everything for this project. We're going to call the project LJ project. LJ again for the application that's running simulations. It was also called LJ. And we're just going to fill this database file, because it's a file, it's SQLite database is a file, with tables. And the tables will refer to one another, and that's okay. And so here's the parameter table. That's going to be our first table, and it will have a number of columns. Now, I want, regardless of what my tables are, they will always have a primary key. So I'm just going to start with the parameter ID that is an integer primary key. So whatever parameter is, there's an ID. I'll give it a name. And since I'm encoding it anyway, this is a good point where I might explain what units everything is expressed in. So I'll have that here, units, and then the lower limit and upper limits. And then I'm going to insert a bunch of parameters. So I'm going to insert a temperature. It will be measured in Kelvin, and I'll go from 80 to 340. This doesn't do it, right? This doesn't make it so. It just records that this is what we want to do, and we'll use these values to generate our scripts later, right? But the application better correspond with how the application, our LJ application, how it expects the parameters to be put in. It can't change that application by just changing the values here. This is more of a record of how things are than anything else. But it does mean, and maybe that's kind of why it's here, it does mean that if I ever gave the database of the whole workflow to somebody else, but not the application, they would still be able to make sense of it. So that is kind of the point. So you can see that some parameters, here's my burn-in. Some parameters are the same in lower and upper bound, so that's the only value that I'll have. The random seed, the time steps, the run times, and the numbers are all the same. But the temperature has a range, and the density has a range. Okay. So I'm going to put those in, commit, and close. Now I've created this file. It has the table of parameters. So the parameter ID there is just in case I wanted ever to have two. Say I wanted a different simulation, not for this one, but another simulation where I start my system in one temperature and I heat it up to another temperature. That kind of simulation would have two parameters. They can both be called temperature, but they would have to be different. Now, you could say that means the name is not correct, but to sort of abstract away or even avoid the possibility of an accidental name clash, I insist on a primary key for basically anything. So here too, I just call. So in that case, the initial temperature might have the same name as the final temperature, but their parameter ID we would be able to distinguish them. Okay, so at this point, because we're doing it sensible and everything has its own unique name, yes, we could get away with not doing it, but then we'd have to use these names all over the place anyway. So it could be sometimes useful to have an integer representation anyway. So yeah, any table that I create, unless it's a table that expresses relations between keys, will have a primary key of its own. Yeah. Okay, so once we've run this, and actually this is a good point to show you how you get there. So let me see if I can change to share my teach cluster terminal. Share. All right, yes, I think I'm here. Okay, so if you guys haven't had access to the teach cluster yet, that means I missed giving you access somehow. Let me know, and I'll get it. Write it in the chat. The chat is saved on my machine automatically, not for others, but so I can later make sure that I add you. If you have a Signet account, mention your Signet username. And otherwise, if you have a temp account on the education site, mention that so I kind of know who's who. Anyway, if you do have access and you have an SSH client, then the following should work. You should be able to type SSH -y will allow graphics to appear on my screen. It's kind of optional, but can be useful. And then the server is called teach.signet.utoronto.ca. I have keys set up so I don't have to type my password every time. It's going to likely ask you for the password, but that's it. So I'm in here. I'm going to go to my Scratch directory. So the Scratch directory is good because you can write to it from Compute Jobs, and that's what we'll need. So we'll go there anyway. And then you can get the code, and you can copy it over. So you do CP for copy, -R because we want to copy recursively a whole directory. And the directory is called SciNet course DBB20. So database basics 20. And we can copy the whole thing over. A dot means the current directory. For if you haven't seen that before, you can also explicitly say you want it to your Scratch. It'll do the same thing, but since I already had it, it's asking me stuff. So in my Scratch directory, I'll have a directory called dbb20 now, and it contains some stuff. So you can see there's already a Python file for generating the parameters. That should be exactly or very close to the code that was just on the slides. There is an input parameter for Argon simulations. There's a second step that we'll look at soon. And here's the code for the simulation. We don't need to look at the code, but we do have to compile it to make the executable. So there's a makefile to help us compile. But before we do that, we have to set up things. So on our clusters, almost all software is in modules, software modules, and we have to load them first. So all that the setup actually contains is a bunch of module load commands. So you can either copy and paste it, or you can say source setup. And then I can do module list, and it'll show me all the lists that are currently loaded. So this is a compiler. We'll be using GNU Parallel at some point, and we'll explain what that is. If we wanted to visualize the trajectories, we could use VMD. It's kind of slow over the internet, so you might not want to do that. We're using Python. The easiest way to get Python on the teacher cluster is to load the Intel Python module. So Intel distributes a version of Python that has a bunch of packages already there, optimized for the Intel chips that we have on the cluster. So might as well use that. Okay, so now that that's there, we have our compiler. We can type make, and that compiles our LJ code into an executable. I can run it, but then it wants to read from standard inputs, so that's not what we want. So we can take this Argon input file, which looks like this. So our Argon input file has a number of things. Oh, LM, Milena, stands for linking the math library. C, this is a C code, and C is an old language, and to link in to use math functions, you have to link in the math library explicitly with -lm. That's all it does. Okay, so here are parameters. It's just a list. The same parameters we can also give on the command line, but we can give it the inputs. So now I say LJ. That's the name of the command. The LJ lives in the current directory. So here's our / saying that it's in the current directory. And then it should start running. Now, an equivalent way of running this would be to put all of these parameters on the command line. What's happening here? Argon outputs are. And I'm mentioning that because that can be a useful way to generate a bunch of simulations. Rather than having to generate 100 files, we just generate 100 commands, which might be a little bit easier. See, it does the same thing. This first parameter is the name of a file, sorry, the name of a directory that it puts its output in. So if I do ls, there's a new directory here called Argon output. And that contains all our output. The output of that has all the data. Well, not all the data. It doesn't have the directory. That's the XSF file. And this is per time step. It gives me the energy, the potential energy, kinetic energy, the temperature, and the pressure. So the pressure particularly. It fluctuates. That's normal. And then the last line of this contains the averages. We saw this last time as well. So here are the averages, and here the average for the simulation of the pressure was 1.62. Okay. That last line is what we'll be after in our application, but we'll generate all the other stuff as well. And that could be useful for another analysis, perhaps, that we want to do. Okay, so that's the application. It can now run, but now we have to generate the SQL file, the database file. So that's a parameters ranges. So this is pretty close to what was on the slide. Instead of an execute many, apparently I did just a whole bunch of inserts. But it's temperature, density, number, runtime, time step, seed, and burn-in. So that should work. Let's try running that. So Python, run the Python. It doesn't say anything, but that probably means it was successful. And did it create a, yeah, here's a file, LJ project.sqlite. Now, I am, and I think you should be too, a little distrustful. There was no output, so it should all have happened okay, but can we please check out this table that we just created? And the answer is yes, we can. With SQLite comes a command called SQLite 3, because this was version 3, and it'll allow us to look into this file. So I give the SQLite 3 command and then the name of the file, and not very helpful. It's a command line, so it doesn't pop up or anything like that. But if I don't know what to do, it gives you the helpful suggestion of typing .help. There's a lot of commands here. Let's try something simple, and like select everything from a table we just created, and a table we created, I think, was called parameters. Right. A bit ugly, but the data is all here. So we have an index, sorry, not an index, we have a key, we have the name, we have the units, we have the lower bound and the upper bound. And there's ways to make this a little prettier, even within this interface. You can say that you want the columns to show. Oh, so that if you do select star again, it shows that columns. It's a bit more readable. You can add the headers. And what is nice, but also slightly dangerous, is that you can really type in any SQL command in here. If it's not an SQL command, if it's an SQLite interface command, it starts with a period. So that's why these are periods. They are not SQL. They are sort of meta commands that change how the SQL is shown afterwards. Anyway, so that's in here. That looks good. Fine. There's another way to do this, and that only really works if you have the graphics forwarded with the -y. But I don't want to not mention this. It's SQLite browser. Now that's a separate application. You might not have it, but the Teach cluster has it. And get my project running. So same thing, SQLite browser, LJ project. And this is graphical, but now I have to change my my share so that you can see it. Okay, so this is a bit small probably for you to see, but it has a list of all the tables. And there's really only one. And then the rest is not real tables. So there's one real table. It's called parameters. Oh, parameters. And I can browse that data. So I can click on the data. And it also will show you the parameters. And I can select different tables. In this case, there's only one so far. And I can execute SQLs as well. So this is a bit more graphical. And you might like that better, but it's they're really good tools to quickly check if you did your setup correctly or if your data makes sense. If you have a database that contains 1 million rows, you don't want to work with it in these contexts. It's just not very productive. But for quick checks, this is pretty good. So let's go back to the. Let's go back to the slides. Okay. Right, so this is what we did. We did SQL that showed this, SQLite. To get out of SQLite, in case you're wondering, .exit does that, because that's not an SQL command. So, SQLite browser kind of looked like this. Depends on your operating system what it actually really looks like, but it has the same data in it. Okay, so that was our first step, but it really didn't do much. It just defined the range of things we want to investigate. Now we want to actually take that and generate specific parameter sets to use in each simulation. Okay, so we're going to need Python's help. SQL isn't very good at generating ranges. If it says no such table, did you run the Python scripts? Are you in the SQLite browser? So let's see. Change the share. Share participants. Here. Okay. So if you have, so if you type SQLite browse or just SQLite 3, and then the name of your database file, and you do .tables, it will give you the list of all of the tables. And I'm guessing if that didn't work, sorry, .exit. Try running Python a parameter ranges one more time. For me, it says the table already exists, but yeah. Also make sure that you've sourced this setup. So if you do module list, you should have this Intel Python in there. We can try towards the end of the session if you still have trouble to do a screen share, and then we can see if it is. Oh, it works now. Okay, then we don't have to do that. Excellent. Okay, so our first step was to create these parameters. The second step is going to be to create the individual sets for each simulation. So I've called that step B. Change my share again. The browser just press the X button, but the SQLite 3 is .exit. So like so. I apparently even .xe works. Okay. Share, new share, new share. Okay, so the next step of our assignment, which we're doing together so far, is to create a second table that is based partly on this first table of parameters, but now actually has the actual sets. We need Python's help to take the ranges that we defined and generate an actual set of data. So we'll keep it fairly simple. We'll do 10 values within the parameter ranges. So the ranges were specified. We do 10 values in each. So we have a range for temperature and for density. So that's going to be 100 values, which is not that bad. We can easily handle that. So one way to do that is just to say, okay, let's open our projects file and let's find the temperature range. So we will do a select. We select the lower limit and the upper limit from the parameters where the name is temperature. We have to Now that gives us a cursor, remember. So we want to actually get the values out. We have to do our fetch one, and fetch one will fetch the first row that this is valid for. So it'll give you a tuple of the lower and the upper limits. That's fine. So we will have those. And then from that, we're going to use NumPy to create a range of values between those. And a very useful utility in NumPy for that is the linspace. So it can give the linspace the lower and upper bound, and then say how many how many points I want in between. So that's going to be an array of t values. Now, the reason there's this funny star in front of it is that fetch1 gives me a tuple, but linspace wants two separate numbers, the lower and upper bound. So star sort of unwraps that tuple into two parameters. That's all that really happens there. So that's a list, or really an array of temperature values called tvals. I'm doing the same for the density. So I select the lower and upper limit, and then create a linspace, so a range of values between the lower and upper limit. Again, t of them and that gives me a set of densities. So I'm calling that densevals. The other ones, the number of particles, the time step, the time to run, and the seed also have to be selected. Also the burn-in time, which doesn't seem to be in this slide either. But they are always the same. And it's not very elegant here, but I'm just assuming that they're always the same. So I'm just taking the lower bound. So the 0, 1 is just the lower bound. It'd be more elegant if I fetch the lower and upper bound, checked whether they are the same, and if they're the same, just do one number. That'd be much more elegant. But okay, elegance is for tailors, as one of my former supervisors used to say. So this works, and so that's good. So n is gotten, t is gotten, dt, and s is gotten. Those are all the parameters, and some of them are lists. And from those, we're now going to create a new table that contains all possible combinations. Okay. So we first create the table, and we'll give a primary key to each of the parameter sets. And for reasons that will become clearer later, the primary key here will not be called ID or parameter set ID, but sec with a capital. So it's a sequence number if you want. The temperature column is a real value. The density is a real value. The number of atoms will be an integer. The runtime will be a real value. So will be the time step, and then the seed, and then the burn-in time should be here too, and that would have been a real number as well. Okay. So those are columns. I have to I have to give rows now. Okay, so for tables, there's never any real sorting defined. But because I'm setting a sequence number, and when I'm inserting them, they will get a sequence number. Basically, you could think of them as being ordered by sequence number. So however, whatever order I put them into the tables in is going to be the order in which they are stored, if you want. Okay. So now in Python, it's pretty easy to generate a sort of a all combinations kind of situation by using list comprehensions. So I want a tuple of parameters. I want a temperature, a density, a number of particles, a runtime, time step, and a seed, and a burn-in. Again, sorry about that. And I want that for every t in the tvals and every d in the devals. Using that, and the other ones are all fixed. But you can see how that would be very easy to extend if n was also an array. You just do more for loops, and you just get a fairly long list. I mean, this is only 100 tuples. It's not memory bound in any sense, but you can make this pretty large. So this is our set of parameters. So it's a list of tuples, and we saw before that's how in Python these tables tend to look. And I can do an execute many into the parameter sets and just put those in. Give it that list. The null here means that my sequence is going to be automatically filled with a value starting from 1 and then up to 100. I can commit it, I can close it. So this generates a table of parameter sets for which I want to do a simulation. Yeah, I think I just forgot to update the slides. I think the code is okay. So we could check that. So I would pop up, say, the SQLite browser, and I'd see something like this. I'd see a parameter sets table, and it'll have proper values for each of the values. A lot of them will be the same. The density can be seen to have a range. The temperature seems constant, but if you scroll down, you would see different temperatures as well. So that's a good check. There's a second step in getting our simulation set up, is that from those parameters we just got, we should create an input file and some sort of job scripts, right? Because each of them is going to be a separate job. Then that's what we should do. So we could now create a script that goes over the parameters, the parameter sets, and for each parameter sets creates an input file and a job script, and then maybe launches or submits that job script to the scheduler. Because of the way that, because it already has a way to store the outputs in a directory. So this LJ thing took a directory name as its first argument. We're going to use that, and that will be how we can distinguish where different output is for each job. But we're not going to do it that way. This is a possibility, but this is a bunch of fairly small simulations, and we even saw when we ran an instance of the LJ application. It's pretty quick. To be honest, we could do this whole project with a simple for loop or nested for loop in a bash script. That's totally true. The point, of course, is that this is supposed to be an example that could scale to something that isn't feasible to do in that way. But still, this is a bunch of little serial jobs. Serial meaning each job just takes a single core on the node. And if you started submitting jobs for that, what happens on large clusters like Niagara, but even on the Teach cluster, is that you would get a whole node. The whole node has 16 cores, but this job is just running for a few seconds on a single core. So that's wasteful because the other cores aren't doing anything. So whenever you're faced with a situation where you have a lot of independent jobs to do, and each of them doesn't need that many resources, rather than using the scheduler of the cluster, you can use something called GNU Parallel. You can also use GNU Parallel on your own machine, so that makes it sort of more portable. That's great. And what it does, it actually takes a bunch of small jobs, looks at your system and goes, how many cores do you have, and starts doling out those jobs to all the cores, or to as many as you specify. It doesn't have to be the whole set, but say that you take the whole set. So it starts spawning 16 jobs of your long list of jobs, and whenever one of the jobs is done, it gives that core a new job to do. And so that keeps all of the cores busy until your list is done. So let's look a little bit more at this GNU Parallel, because it is very handy, but it does have its own syntax that it is worth explaining and showing. So imagine that I wanted to look for the word JFK in a set of files. I could do that by just giving, so in Linux, you would look for things inside a file with the grep command. So the grep command searches for the occurrence of JFK. This is -L. -L means just list the file name rather than giving me the match inside the file. So that just gives me a list of the files. Now, I could give grep the whole list of files, and it just does them one by one. It will take the first file, starts looking for JFK, the next file, looks for JFK, etc. If I have a multi-core machine, which almost any machine is these days, that isn't using or utilizing the machine to its fullest. If at the same time you're running some other stuff, so it's on your desktop, you might not care. But if you're running it on a cluster, you'd want to use all the resources, because otherwise you're just wasting things. and you'd be slower. So say I have a 4-core machine, what I can do instead, say I wanted to look for JFK in all files called something.csv, then I can use the find command in the current directory to find everything that has all CSV files. That produces a list, and I can pass that list to GNU Parallel. The command associated with GNU Parallel is just parallel. I can tell it how many cores I want to use, or really how many of these I'm going to run at the same time, and then a command. So the command is run, but implicitly there's an extra arguments given to this command that comes from the list that I piped in on the left. So this is one way to use GNU Parallel. You find the set of lists, so the list of files, you pass that to a command, but with the parallel command in between, it actually runs 4 of those commands at the same time, so it's done 4 times as fast. That's great. It keeps the system busy. Now that's one way to use it. You basically just pipe in the arguments that you want. There's other ways, and ways that are very useful in parameter sweeps. So what we're doing here for our argon gas is what's called a parameter sweep, because we're sweeping in temperature space and in density space, and that's a fairly small sweep, but it's still a sweep. So that's what it's called. So GNU Parallel can do the following. Let me show it first, and then you'll see why it's useful. So here's the parallel command again. Here's the base command, echo. Echo prints something to screen in Linux. And then I can give it arguments, but it doesn't have to be just one argument. I can give it multiple arguments. So here's a list of arguments, 1, 2, and another list of arguments, AB, and another list of arguments, exclamation, question mark. And each argument list is prepended with 3 colons. So that's the syntax. The 3 colons mean here comes a list of parameters. The parameters are separated by a space, as is fairly common in Linux, right? So here's our first set of parameters, second and third. And what it does, it takes all possible combinations of these. So that's why what the output is 8 lines. The first line combines the first parameter with the first parameter with the first parameter, the second, the first with the first with the second of the last line, etc. So all possible combinations. And that's exactly the kind of thing we will want here. We'll have densities, 10 of them. So that's a list of 10, and another list of 10 temperatures. And we want basically every possible combination. That will be exactly this kind of a situation. So there's a question whether GNU Parallel can take advantage of hyperthreading. And I'll answer that once I've gone through the slide, but in essence, yes. One other nice thing why GNU Parallel works well in the current context is that it actually can use SQLite. You can not only create these cross products of parameters, you can ask GNU Parallel to store those into the database with 1 row for each job or sub-job, as we like to call it, that GNU Parallel is going to run. And so that sort of automatically gives us this possibility of record keeping of each job. And not only that, it will also, when you have GNU Parallel do that, it will create this table, but this table will have extra columns that will tell you after the job has run, whether it was successful, how long it ran, and some other properties of the job that will actually tell us if any of them failed. So in sort of hands-off computing, like batch computing is, this can be very important. Your job might fail, but maybe it's just one of the 100 jobs that failed, and you'd want to know which one that is to investigate what went wrong, rather than having to slowly narrow down and try each and every one of them and see, well, they're all successful, and then the 100th one failed. So that's useful. But the way it does is by doing a 2-step approach. And we kind of have the same 2-step approach in mind anyway. The first approach is to create the table of parameter sets. And the second one is to actually run those commands that correspond to that parameter set. Okay. So the first part is to do it gets invoked by doing -SQL master. Master here just means that it creates this master table of possible parameter sets. It doesn't actually run them. So it is a fairly fast process. But it really has in mind this idea that these are going to be done slowly and in the future. So this prepares our table. We have to give it a database file to express that it is a SQLite3 database. We have to prevent it with SQLite3 : / it can use other databases as well, but we're not going to get into that. And then within that database, you have to say what table it should use, what the name should be of the table that it will generate. In SQL, but in the actual case, I think we call it parameter sets or something like that. And then this is our command. Now our command is going to have some version of the LJ command, but this is the thing that corresponds to what the left is doing here. Once this is stored, we can run it by invoking parallel again, now with SQL worker. So now things are going to get working. And then again, you have to say what table it takes. So now, rather than specifying on the command line what the commands are, those commands are already in this table, and it just now does them one at a time. And it also keeps track of what's done, how long it took, the parameters that were passed to it. So it knows that there are 3 parameters here. It'll have a column for each of the parameters, as you would expect, and all of those are stored. So it's kind of nice and fits well within this scheme. So to come back to this idea of hybrid threading, by default, GNU Parallel will try and use as many cores as the operating says that there are. Now, this thing of hybrid threading is a way to have, say, 4 cores on a machine or 16 cores on a machine and have them pretend like they're 32 cores. It's something that is done fairly frequently on some Intel chips. And the idea here is not so strange. Most applications, or a lot of, especially in sort of the desktop world, when one application is doing, say, a computation, another application might be writing to disk, another computation might be showing something on screen. Those are all actually different bits of hardware working on the chip that can run in parallel. So you could have, now if you only ran as many processes at the same time as you have actual chips, you're not using those subparts of the chips very efficiently. So hyperthreading is basically a way to utilize that. But rather than having the operating system know exactly how the chips are, it just presents itself as if there's twice as many cores in the machine. So on Niagara, for instance, each node has 40 cores. But if you ask the operating system, so if you ask Linux, it'll say that there's 80. And so GNU Parallel will by default use 80 cores. It doesn't know any better. It says, well, the operating system says there's 80, so I'm going to run 80. So by default, it will use hyperthreading. You can, on some systems, the system administrators will have switched this off. So the number of cores and the number of the parent cores is the same there. But it's often advantageous to use hyperthreading. So we have it on by default. Not on the Teach cluster. The Teach cluster is kept somewhat simpler, but on Niagara it works like that. You can yourself use hyperthreading even if it's not enabled, and this can give you some speed up. But then you have to tell Parallel to run more than the number of cores. So if the number of cores was 40, say, and you want GNU Parallel to run 80 things at the same time, hoping that somehow it'll balance out, it might. You can do the -J option. So I think we had an example here. So -J/4 will run 4 things at the same time. Okay. So those are extra parameters. There is a lot of parameters that you can give to Parallel. Most of them have to do with how you create the jobs, but some of them also with how many you can run at the same time. Okay, so now that we have that, we actually have those 2 steps of creating the job, the parameter sets, and the runs more or less at the same time. So we're going to use that. And that makes our our script substantially uglier. Now there's two parts. So the first part is essentially the same, as you can see, right? I'm still using those parameter sets. But the second part has GNU Parallel do essentially the same thing to generate our next table. And our next table will be called jobs. So here's jobs. So we had parameter sets, that still exists. But then rather than taking those and then creating things, we'll use GNU Parallel. Now, the reason it's a little ugly is that we now have sort of a combination of Python and SQL and shell scripting called from within Python. That's why it's ugly. Okay, it's not doing weird things, but it does mixing all those languages is always it will always look a little bit funny. So the way I've set it up is that I'm creating a list of things that I want to be the arguments of a shell command. So GNU Parallel is a shell command, and so that's the first one. Then there's a parameter, SQL master. Then there is a argument that says where to store things. That's jobs. There's an argument that says the next thing that follows is the command that has to be generated into the table. So that's LJ, and then all the parameters. And those parameters themselves can have numbers. It doesn't that's and by doing that, let's start that again. On the command line, let's go back to the command line. I can have several of these parameters, right? Now, by default, it will paste them after the echo command in order. But I can also, instead of that, use it sort of a templated version where I have some commands and there are substitutions of these parameters. The substitution token is curly brace and then a number in between. Curly brace 1 is a number from the first set. Curly brace 2 is a number from the second set. Curly brace 3 is from the third set. So I've done it explicitly. In addition, there is a special sort of implicit parameter that you don't see here, which is the sequence number. Like this is sequence number 1, 2, 3, 4, 5, 6, 7, 8, and then it's done for this case. That sequence number is also tokenized by a curly brace thing, but with a pound sign. So what I've got here is that I have my first argument to the LJ command be whatever the sequence number is of this set of commands. And that, according to how the Leonard-Jones, the LJ command works, is going to be also the directory name in which things are stored. So I'm doing this so that every job will have its own directory in which things are stored. And the directory name is just going to be a number. We could get more fancy, but we really don't need to. So that's all that this does. Then after that, I have to have an argument that says what type of system we're doing. We're doing Argon, so AR. And then all the other parameters come. And just to be explicit or to allow for future cases where I might have to invert some of the parameters or insert them, I'm being very explicit in saying curly brace 1, curly brace 2, curly brace 3, curly brace 4, 5, 6, 7, which is really the parameters out of this. I think the actual B prepared job format will have a better value for the burn-in, but there's a burn-in here mentioned nonetheless. Okay, so these words are now joined with a space, and that gives me the command I want to run. And it's actually it's running here. So this subprocess is a way to run a shell script or a shell command from Python, and that's all it does. It will have produced, once it says run, and we wait for it to finish. Once it's run and wait to finish, it will have produced my jobs table with all of these parameters in it, and GNU Parallel will be able to use that jobs table to run the actual simulations. How will it do that? Well, for that, we also created a command. So it's the same kind of idea, but now here's our SQL worker. And all that really needs is to have the number of to point at the jobs table. I'm adding an additional parameter here, the -j, to say how many tasks I want to run, and just to keep it general. I don't have to do that. It will figure it out by itself. But I want to set this to the number of tasks, the number of cores given by the Slurm scheduler. So this, yeah. So what will happen is that it will actually create two things. It'll create the jobs database by running the GNU parallel prepare command, and it will then create a second script, which is a batch script or job script called C run jobs, and it will put some stuff in it. What it will put in it is essentially this. So it generates not just the table, but also the job script to run that table. And job scripts look like this. So job scripts will have to ask for a certain number of nodes. Yeah, I'll get to what the %x stands for. A certain number of nodes, a certain number of tasks per node. This is going to run the teach cluster, so 16 tasks per node makes sense, but we could try the hyper-threading kind of idea by having more. These are such short jobs, you're not going to see the effect, but you could play with this in real situations. How long the job should run for? 1 hour is very comfortable here. It doesn't take 1 hour, but just, you don't want it to be too little because your job gets killed and your simulations are incomplete. You can give it a job name. I'm calling it C run jobs, and that pops up in the queue. When I look at the scheduler queue, that's the name it will be under. And then I can change where output is written to. And that has some templated versions as well. So %x actually gets replaced by the job name, and %j is replaced by the number of the job in the queue. So every job that runs on the cluster gets a successive number. It's kind of like a primary key, and so that gets appended to the output name. So that's asking for the resources and where the output should go. The rest is saying what actually should happen when this job is running. It should source setups where all the modules are still there, and then run parallel, SQL worker, SQLite 3. In this case, we would have probably just typed it by hand. The fact that the B prepare job script also generated it was a little bit superfluous, but I just wanted it automated. So we can look at whether that's working. Let's change the share. Let's run B. And it ran. And did it work? Oh, let's look. SQLite. Let's just do 3. So I have the jobs parameter sets and parameters, and I can just select everything from jobs. This is going to be a bit messy, but there are some things that have no value, and I think that's why it has these funny signs. But it is filled. It's not very pretty. Okay. Seems to have done something. There's a question whether this is one script for 100 jobs, and that's true, exactly. Because these actually only take a couple of seconds, but even if they just take a few minutes, having a separate script for each of them would mean that each of those scripts has to be scheduled, and scheduling has some overhead. So it would actually take longer to find a resource to run things on than to run it. Whereas in this case, we can just ask for one node that is found once and then just run things on it. So that's there. Yeah, in parallel, ideally, I have to admit, ideally you'd have a scheduler that can sort of do this rather than have a separate command. But schedulers are very, very busy with figuring out what should run where, because often they also have to take into account whether there's groups with priorities, or whether there's users that have already run a lot, and so they should run a little bit less, so other users get a chance. So there's a lot of computation in scheduling, um, which is why it takes time. So having the parallel command there to just ask for a larger set of resources that you're going to use anyway, and then run small jobs is very neat. It's also very neat to just run on your own machine. Like it really is. It's pretty nice. So where we are, yes. Oh, let's look at the scripts for a while. Yeah. So yeah, it does essentially the same thing. It creates. Yeah, here this part we've seen, right? We created the parameter sets. Here's that same GNU parallel command that I did with the join. I'm doing the join just because this is a matter of taste, but having all of these separate lines sort of keeps things clear in my head. Like these are just all of the words that are going to be passed to the shell. Yeah. And our join commands, running things. Yeah. Okay, so now we could actually run this. Let's try that. So the way you run a script like C run jobs is you could run it just like that, but you don't want to do that because this is supposed to be a schedulable job. So you give it to a command called sbatch. That's because it's Slurm. Other schedulers have different syntax. They'd also have different syntax in how you ask for nodes and tasks and stuff. But once I do that, it says I submitted a job. Now I can see in the queue where this is, 3913, and it's running. R means it's running. And you can see it's starting to generate directories for each of the cases. So as it's running, the number of directories is going to keep increasing. Is it done? It's still running. This is not possible everywhere, but for our cases, we can actually log into the node that it's running on. It's called teach02, and let's see, and type top, and we can actually see things running. It's pretty nice. We can see the 16 things running at the same time. An even nicer command is htop that shows all processors being used. And then we're hitting the end of the list. The 100 is not divisible by 16 exactly, so for a little while it will be underutilized, but not for very long. And then it's done. So let's look at SQLite browser and see what it did to our command. So we now have more tables. I know this is small, but this is the table called parameters. We had that in the beginning. This is our table called parameter sets. And then there's our table called jobs, which was generated by our friend GNU Parallel. And GNU Parallel is the one that decided that the first, the unique key is called sec with a capital. That's why that was chosen. So let's look at the data in jobs. And here we see the data in jobs. So it has, I'll read it to you because I can't imagine you can read that, or you might have a really big screen. So the sequence number is there. It told us what host it was running on. We might not care too much, but it was running on teacher2 when it started, how long it took. So this took 8 seconds. Some took a little longer, some a little less. These are bytes that were sent or received. it doesn't do that. The command that was run, so that is useful for record keeping, and it has all of the parameters if you increase the size. And then each parameter has its own column. Now, unfortunately, GNU Parallel doesn't know what these columns should be called, these parameters. So it calls them v1, v2, v3, which corresponds to the curly brace stuff, right? So that we can make the mapping back, but yeah, GNU Parallel doesn't name these things. So that's a little bit unfortunate. And then it has the output as well. Now, most of the output goes to files, but some of the output does not. So we can actually see the output of each command, and it starts out with ID, and then it has some other stuff. There's one more thing that I wanted to see here. Let's see, where's this? Oh, yes, the exit value. So the exit value will be 0 if it is successful. So the fact that these are all 0 is excellent. It means that all of these ran successfully to completion. There is, and I forgot exactly what the syntax is, but there is even a way to tell GNU Parallel if some of them were not successful. Maybe you ran out of time, you asked for an hour, and it took more, to take the same database and just run the ones that were unsuccessful, and to basically try again, because it has the records already, and it can do that. But I forgot what the exact syntax for that is. Maybe something like dash resume or something like that. But you can look that up. Okay, so that's going well. We have managed to put job description, so parameter ranges, parameter sets, and jobs descriptions in there, and use those to run the simulations. Let's see what is next. Here. So next is your job. So what I'd like you to try and do is rerun this. It should be fairly simple, because if you copy things and you run those A and B scripts, and then sbatch the C script, it should run. And so try that first. And then you have the data there, right? It's in the directories. You have the table called jobs that has a record of every job that was run, with all the parameters in there. So but it doesn't have it. But what it doesn't have is the output, because the output was things like the pressure, and that's in files that are in directories 1 to 100, right? So so write a new script, Python script, that reads those jobs from the jobs table, and then goes and finds the actual output of those jobs, and make a new, a new table with per job the measurements. So the average pressure and the average energy, basically everything in that last line, all the averages, put those in the table called measurements, and link them to the sequence number, essentially the run number of the job. So that's collecting the measurements. And once you have that, so now you have the job descriptions, you have the parameter sets, you have the output, you have the measurements. You should be able to do step E as well, which is analysis. So write yet another script that can select measurement data from the database, from say the lowest temperature. Just you could do any temperature, but just to be explicit, the lowest temperature, which was 80 Kelvin, and plots and get the pressure versus density. So get those. So for every density that we ran, we should now have a pressure in the measurement column in the measurement table. So get those, and then make a little plot or write a table. You're in Python anyway, so plotting it is pretty simple. It might be nice to see how for that particular temperature, the pressure depends on density. If this is easy for you, try it for different temperatures and see if there's any temperature that causes maybe a phase transition or something. But if not, just at least try and get going on those two. So start with D. If D doesn't quite work, of course, E is sort of impossible. But as I said, what we're going to do is I want you to try this at home. try and submit something before midnight tomorrow. That will give me a chance on Friday morning to look at it, to look at what you did, and to sort of address common issues, but also show you how the solution would go, and then you can try it yourself and either resubmit on Friday or call it a day. But that's okay. So for the plots, whatever you want. Okay, so there's a few good questions here. One of one of them is graphics, what you use. Don't really care too much. GNUplot, Matplot, whatever. If it generates a PNG or a PDF or something on screen, because the script, I will just run the script and we'll see if it works. That's fine. But yeah, if you have like about 10 graphics, that is also fine. Maybe you want to combine them. Don't go too crazy. Really, but if you want, sure. About the errors of home not being writable. So that's important to get the SBatch to work. If you copied your the dbb20 directory onto the Scratch directory, you wouldn't get that. Home is read-only on the compute node. So when you do SBatch, it can't write to home. That sounds strange, but it is because there's many more compute nodes than any other nodes. And if they all start writing at home on home at the same time, the home system sort of craps out, or at least becomes very slow. So what you want to do is copy the whole thing over to Scratch. So you have a Scratch directory, and then so cd $scratch and do it in there, and you'll be fine. If you have any other questions, I mean, I can stick around for a little while, but if you have other questions later today or tomorrow, either email or I could start a forum on the site as well. But just email me, and I'll try and answer the question when I have a chance. Does it make sense? Okay, good. See you on Friday then.